Hello everyone. Today we're going to go over the other type of electrochemical cell. Last lesson we went over the voltaic cells, which remember, think voltage, they produce electricity, they convert chemical energy to electrical energy. It's a battery essentially. Today we're going to go over the other type of electrochemical cell, which is called electrolytic cells. So we talked about these a little bit in the last lesson. These are basically the opposite of voltaic cells. So electrolytic cells are where electricity is used to drive a non-spontaneous redox reaction. Doesn't happen by itself. You need something to get it going. All right, so we'll see what that is in a little bit. So another name for this is electrolysis. Lyse, in this case, means to break, or we're talking about breaking bonds, right? We're breaking bonds with electricity. So electrolysis means we're using electricity to break bonds. So we can think of electrolytic cells as converting electrical energy to chemical. So we talked about that in the last lesson too. That's the easiest way to describe what electrolytic cells are and what they do. They convert electrical energy to chemical. So they're essentially the opposite of our voltaic cells. So there's a couple of applications here. So one is electroplating. So electroplating, we're using electricity to deposit a thin coating of metal on an object. So that's electroplating. So the Regents likes to show you diagrams here, just like our voltaic cell diagrams. We get diagrams of these electroplating processes, and that's what we have here. So let's take a look at this, and we're going to go through and fill in the appropriate points, and you can kind of use what we went over yesterday to help you out here. So what's going on here? So let's take a look at this diagram. So we have copper is our piece of metal, and then we have a coin. So it's made of nickel, so it's like a quarter. So think of a quarter here, and we want to coat this coin with copper, electroplating. All right. So what are we going to do here? So notice what we have in the middle first. We have a battery. So that's our power supply. So these we're always going to need a power supply. Right? Why do we need a power supply? Because it's non-spontaneous. It doesn't happen by itself. So we need something to get it going. So these are always going to have some outside power supply. In this case, it's our battery, and you're going to see that plugged in there. All right. So the same rules we went over yesterday are going to apply here, except when it's an electrolytic cell, we don't use table J. All right, so we don't use table J here. So you'll see how we figure this out as we go through. So first thing, let's give our uncombined elements their zeros. So copper gets a 0, nickel gets a 0. All right, so those are our electrodes. So now who's who? Who's the anode and who is the cathode? So again, we're not using table J. So how do we know who the anode is and who the cathode is here? Well, when you get one of these setups, what you want to remember is copper is the anode. And how do I know that? Nickel is the cathode, which is the site of reduction. How do I know that? Because the object is always the cathode, right? This is what you want to remember here. The object is always the cathode. So don't use table J. So no table J here. All you want to do is go by the diagram, whatever the object is. So it'd be a coin, sometimes it's a fork, a spoon, a ring, whatever. So the object is what you want to coat with the other metal, because remember, fat, red, cat, right? Whatever the cathode is gets bigger. So why does it get bigger? Because you're coating it with the other metal. So that's why the object is always the cathode. That's what you want to coat with the other metal that's making up the anode. All right. So same thing we went over yesterday. Anox and red cat. The anode is the site of oxidation, and the cathode is the site of reduction. Okay. And electrons always flow away from the anode. Like I said, the same rules that we went over yesterday apply here. However, the only difference is we don't use table J. All right. So, first thing you want to remember is one. So let's go over this stuff. We'll write it down here on the bottom. Object is the cathode. Right. That's what's different from our voltaic cells. But everything else is the same. Two, electrons always flow away from the anode. All right, electrons always flow away from the anode. Other thing is, same as with our voltaic cells. Remember, we want to remember anox and red cat. Right, the anode is still always the site of oxidation, and the cathode is still always going to be the site of reduction. And then the last thing you want to remember is same stuff we went over before. Leo says grr. So all this stuff is the same as voltaic cells. Right? The only difference is number one, we don't go to table J. Right? I wrote that up top. I'll write it again down here. No table J. All right. So now let's go back up here and finish off what we started. So how do we know who the anode and the cathode are? The cathode is always the object, so that makes the other one the anode. Anode is still the site of oxidation. Cathode is still going to be the site of reduction, and electrons always flow away from the anode. All right. So now what's going on here? So notice the difference between these and voltaic cells. They're not in separate containers. They're all in the same container, right? Because when we put these in contact with each other, nothing happens because it's a non-spontaneous reaction. So even though they're in the same container, we're not going to get a direct movement of electrons. So same thing as yesterday, though. Same general principles are taking place here. Copper 0 is the anode, so that's oxidized. So copper 0 is losing electrons and becoming a copper +2 ion. So when it loses electrons, it goes into solution, and it sends those electrons up, over, through the wire, and down, and then those electrons build up on the cathode, just like in the voltaic cell. Okay? So now, what does this positive copper ion do? Remember, opposites attract. This positive copper ion says, hey, look at all those electrons. I want those electrons. So then it moves over there, picks up those electrons, gains those electrons, and gets reduced and deposits itself on the coin. So that's how we coat that coin with copper. When the copper ions get reduced, they pick up those electrons and deposit themselves on the coin. So fat red cat, right? The cathode's getting bigger because we're depositing those ions from the anode on that object. It's that simple. Okay? So what's taking place here? The anode now is positive and the cathode is negative. So if you notice, this is flipped from what took place in the voltaic cells. But easy way to remember, just look at the battery. Look and see which end of the battery you're hooked up to, right? The copper is hooked up to the positive end. So what's the charge of the anode? Positive. The cathode is hooked up to the negative end. So what's the charge of the cathode? Negative. It's that simple. So with the electrolytic cells, just use the battery to figure out the charges of the electrodes. All right, positive end is positive, negative end is negative. That's simple. So next thing we want to do is look at the half reactions and who's oxidized, who's reduced. So who lost electrons? Copper, but specifically copper 0. So copper 0 lost electrons to become copper plus 2 ions and the 2 electrons that it lost. Now, who's getting reduced? All right, so the nickel is the cathode, but you want to think about who is actually gaining electrons. The nickel is the cathode, it's the site where reduction is taking place, but who is actually getting reduced? The copper ions. Copper plus 2, those ions are gaining 2 electrons to become copper 0. All right, so don't get confused by who the cathode is. Think about who is getting reduced. The copper ions are getting reduced because they're gaining electrons and becoming copper 0 and depositing themselves on the cathode. All right, in this case, it's a coin, and that's how we would electroplate that coin and coat it with copper. So what do you notice here? Notice the oxidation and reduction half reactions. They're kind of just opposite each other. So just keep in mind, it's the same element. So the same element that gets oxidized, the ion gets reduced, just like with the voltaic cells. Same exact thing. The ion gets reduced. Who's gaining those electrons specifically? So that's pretty much it with these diagrams, and we'll sum them all up again in a few minutes. So what else are electrolytic cells used for? The purification of metal. So if we have some silver that's tarnished, right, we can then reverse the process and remove that tarnish that essentially it's kind of like rust that builds up on a piece of silver, and now it's nice and shiny again. So another way that these electrolytic cells are used is preparing active metals. So think about when we talk about like pure sodium, pure chlorine, these are reactive. They are generally found in compounds in nature because they are so reactive. So how do we ever find them alone? Well, we don't. We have to make them. So if I have some NaCl, I can use energy to break these bonds in NaCl into Na and Cl, Cl2, right? So also electrolysis of water, we call that a Hofmann apparatus. So here's the process here. So we take water and we break it up into hydrogen and oxygen. So we can break those bonds in a water molecule between hydrogen and oxygen and separate them into H2 and O2. Right? That's another way that this process is used. All right, don't worry about that stuff. And then finally, let's just kind of sum things up here. So let me move myself out of the way here a little bit. So let's take a look at the electrolytic and the voltaic cells side by side and do a little comparison. So this is the last thing that we're going to look at here. We'll take a look at these side by side. And compare them. All right, so let's start off with the voltaic cells. So how do we know it's a voltaic cell? Hey, it's got our salt bridge. So look for the salt bridge. So when we're looking at the voltaic cells here, first thing we want to do is figure out who the anode is and who the cathode is. So what do? Well, It's a voltaic cell, so we want to go to table J. So who's higher, magnesium or zinc? So we look on here. Here's magnesium, here's zinc. So magnesium is higher. So remember our rules. The higher metal is the anode. That's the one that gets oxidized. So that makes Mg the anode, which is the site of oxidation. And then Zn, zinc, is the cathode, which is the site of reduction. So that's all just starting off with looking on table J. And then what else do we know? Electrons always flow away from the anode. So they're going to go to the right here. And again, remember what's going on. So Mg is losing electrons. It's oxidized. So those electrons then go into solution, sends those electrons up, over, down through the wire, and then they build up down here on the cathode. And then the zinc ions say, hey, look at those electrons. I want some of those. So it goes over, picks up those electrons, and then deposits itself on the cathode. So that's why we say fat red cat, right? The cathode is getting bigger because we're depositing those ions onto the cathode as they are getting reduced and becoming zinc zero atoms, right? So that's the whole process that's taking place here. And that allows for the flow of electrons, and we can use those electrons to do work. So who's the anode and who's the cathode? Well, let's remember our charges first, right? The anode is negative, cathode is positive. So who's the anode? Magnesium, right? That's where our oxidation is taking place. But it's, remember, the anode is a metal. It's a solid object, right? The electrode is a solid object. So magnesium solid is the anode. And what's the oxidation that's taking place? Well, Mg0 is becoming Mg plus 2 by losing 2 electrons. And then who's the cathode? The zinc metal. So what's the reduction that's taking place? Well, the ion is gaining 2 electrons to become zinc 0. And then is a salt bridge present? Yes. And then what's the direction of electron flow? To the right. So also with the salt bridge, remember what's the purpose of the salt bridge? Migration of ions, right? That's the job of the salt bridge. It allows for a migration of ions so that we can maintain neutrality in each of these half cells so that electrons can continue to flow. All right, so we can get a continuous flow of electricity, and those electrons can then be used to do work. So how does this process occur? Spontaneously. Once these substances are in contact with each other, the reaction starts. Right? We close the circuit and we get a flow of electricity. All right, so these are what batteries are. So essentially, voltaic cells are batteries. Batteries are voltaic cells. Right? So now the electrolytic cells are a little bit different. Right? These have a battery. So remember, these are not spontaneous. These, as we said before, and we wrote down, right? These need a power supply, right? Don't forget that. They are not spontaneous, and we'll come back to that. So again, who's the anode, who's the cathode? Well, we don't go to table J here. So we know that the silver is the anode and the spoon is the cathode. Why? Because the object is always the cathode. The object is what we want to coat with the other metal. So anox, red cat, still applies. What's taking place here? Electrons flow away from the anode, same as in the voltaic cell. But now in this case, Ag is losing electrons and becoming Ag ions. Those electrons build up on the cathode. Those electrons build up on the cathode. Then these positive silver ions say, hey, I want some of those electrons. They go over, gain those electrons, and get reduced and deposit themselves on the object. All right? So who's the anode? The anode is positive. The cathode is negative. So notice, that's one of the few differences here. Charges flip. But again, just use the battery to help you out. Positive end, positive anode. Negative end of the battery, negative cathode. right? So look at the end of the battery that it's hooked up to. For the voltaics, just use the direction of electron flow, right? If electrons are moving away from the anode, like charges repel, so negative electrons are being pushed away from a negative anode. Opposites attract, so the cathode we say is positive because the negative electrons are being attracted towards the cathode. So they're not actual charges. They're just kind of ways of us keeping track of which way the electrons are going. So now back over to here. Who's the anode? Ag, solid, right? It's your electrode. It's a solid object. So what's the oxidation that's taking place? Ag0 is becoming Ag plus 1 by losing one electron. Now, the next part, be careful. Who is the cathode? The cathode is the spoon, the tin, Sn. But who is getting reduced? Think about what you're coating that spoon with. We're coating it with silver. The ion gets reduced. So Ag plus 1 gains one electron to become Ag0. So even though the spoon is the cathode, that just means it's the site where reduction takes place. The object is the cathode, but the substance that's actually gaining electrons and getting reduced is the silver ion, right? So that's it. So is the salt bridge present? No, we don't need a salt bridge in an electrolytic cell. Electrons are still flowing away from the anode, but this process is non-spontaneous. That's why we need a power supply. We need something to power this process. This battery pulls those electrons away from the anode and pushes them onto the cathode. So that's powering this process that would normally not occur. If I just took a spoon and dipped it into a silver ion solution, nothing would happen, right? Because the silver is not strong enough to replace the tin, right? So it's not strong enough for this process to occur. So we need the battery. We need some outside power supply to make this non-spontaneous process happen, right? So this is a good side-by-side comparison of the two types of electrochemical cells, the voltaic and the electrolytic. And that concludes this lesson. See you all next time.